Welcome back to Discrete Math. I'm Dr. Jeff Groh. In this lecture, we begin by discussing the representation of Boolean functions. It's based upon a couple principles. First, Boolean functions may be written as a finite combination of three operations: Boolean sums, Boolean products, and the complement. Note that just as with logic, we do not need really all three of these operations. So actually, only two are required. And just as with logic, you can take the plus and the complement, or the times and the complement, and using those you can construct everything else. As an example, suppose we're given the following diagram for a Boolean function. Let's see, for x it's 1, 1, 0, 0, 1, 0, 1, 0, and for f, 0, 1, 0, 0. How can we use these basic operations to construct this operation here? As you can see, the only way you get true is if x equals 1 and y equals 0. That's the only way you get 1 as an output. All others are 0 output. So one way of thinking about this statement is that we have an AND here. AND corresponds to the Boolean product. So basically we're saying if x is true and y is false, that's when we get 1. This gives the following representation. F of x comma y is x times y bar. And we can check this. If they're both true, the only way we can get a 1 out of this if both x is 1 and y bar is 1. That's the situation here. If either of these is false, you'll get a 0. And if they're both true, if y is true, then y bar is false. That's a 0 times 1. That gives you 0 as well. So we can translate this sentence about when you get 1 into a representation for the function itself. Let's try this again with another example. Suppose the outputs are 1, 1, 0, 0. As you can see, we'll get a 1 output when both x equals 1 and y equals 1, or x equals 1 and y equals 0. Those are the two outputs that give you 1. And we can combine these by saying and is times or is plus. So x and y are true, or x and x is true and y is false. X is 1 and y is 0. So this would be a representation, this Boolean function. In framing this discussion, we need a few terms. A literal is a Boolean variable or its complement. Also, a min term of Boolean variables x1, x2 to xn is a single term involving a product of these variables or their complements. So in our first example, we have a Boolean function represented by a single min term involving two literals, x and y bar. But the second function was a function composed of two min terms. The first term involved two literals, x and y. The second term involved two literals, x and y bar. So note a Boolean sum of min terms has a value of 1 when one of its min terms has a value of 1. This fact allows us to easily write down a representation of Boolean functions. The representation of a Boolean function obtained in this way as a sum of min terms, where the value of 1 will be the result of the function when exactly one min term has the value of 1, is called the sum of products expansion. It is also called the disjunctive normal form. This kind of makes sense because the sums in Boolean functions represent OR statements in logic. In this next example, we want to write the following function as a sum of min terms. We can use the distributive property but for min terms in this case, each term needs to involve x, y, and z. This first term doesn't have y in it at all. However, we can think of it as follows. Since y doesn't matter, we can put a product in here and y or y conjugate. And over on the second term, we can put x or x conjugate. We'll use the distributive property again to get xyz plus x y bar z bar plus xy z bar plus x bar y z bar. Now we have 4 min terms that make up this function. And I forgot to put a little bar here. That was a z bar on this particular term. Note that this term appears twice in this expansion. Well, using the principle that in Boolean arithmetic 1 plus 1 equals 1, we don't need both of those terms. One of them will do. So these three midterms are all that are required to express the original function as a sum of minterms. It is also possible to express Boolean functions as a product of Boolean sums. Giving the product of sums expansion. This can be called the conjunctive normal expansion. And that kind of makes sense because Boolean products correspond to the word and, which is conjunction. Since every Boolean function can be expressed using a finite number of sums, products, and we say that the set of operations plus, times, and complement is functionally complete. And so every function, Boolean function, can be expressed by a finite number of these operations made in combination. However, note, use less. We can use plus and conjugate, or we could use times and conjugate. For example, suppose our function is x times y. How could we express this using plus and conjugate instead of times and conjugate? Well, the answer comes from the fact that when we take the conjugate of a sum, the conjugate turns the sum into a product. And then the double complement will yield a double negation, and hence this will be equivalent to this original expression. So we can see that this set is functionally complete. We can replace every product with sums and complements in this fashion. Alternatively, how do you convert this sum into products and complements? And the answer is pretty easy. We use the same principle. The complement turns the product into a sum, and then we have a double complement or double negation, which cancels out, leaving the original expression. Therefore, since we can always make this replacement, times and complement is functionally complete. We should make a special note that plus and times is not functionally complete. And the counterexample proving this would be x bar. How do you express x bar, the complement of x, using only sums and products? And the answer is, you can't. We have two sets of functionally complete operators. Those sets involve two operations. Is there a smaller set of functionally complete operators? And the answer is yes, or else I wouldn't have raised this issue. But we have to introduce a new operation, NAND. Think of this as not and. And we sometimes denote this by a vertical bar. So for instance, one NAND 1, this is the not and, this is going to output 0. One NAND 0, this is not and, we don't get both of these true, so we'll output 1. Similarly, 0 NAND 1 is 1, and 0 NAND 0 is 1 because we don't have the AND situation here. So the NAND operation by itself can be used to construct Boolean functions. There's another operation called NOR, or not or. And it's denoted by a downward arrow. So one NOR 1 will produce 0. One NOR 0 will produce 0. 0 NOR 1 will produce 0. And 0 NOR 0, that's the only case in which neither of these gives you a true result, false or false. That's going to be 1. That satisfies neither of them are 1, and so it'll output true. So these sets, NAND and NOR, are functionally complete. To see this, note that X complement is the same as X NAND X. You can see that if X is 0, X complement will output 1. Whereas 1 not and 1 will output 0. If I put in 0 not and 0, that gives me a 1. They're not both 1, and hence you get 1 in this case. So you get exactly the same table for the Boolean function X complement versus X NAND X. So complements can be replaced with a single NAND operation. But what about sums or products? It turns out that X times Y can be represented by X NAND Y, NAND X NAND Y. A little more complicated. You kind of expect that. The simpler a language, the more elements you need to put in there in order to express a single concept. The more complicated the language, the more tools you have, the more efficiently you can express various concepts. To see this, suppose that X and Y are given, with X times Y, and then X NAND Y, and then X NAND Y NAND X NAND Y. X times Y will get 1, 0, 0, 0. So what about X NAND Y, not AND? So here we have both together, but it's not AND, so it'll be 0 here. On each of the other ones, you get not AND to be true. So what about this NAND itself? 0 NAND 0 will be 1, not AND. 1 NAND 1 will be 0 because it's not AND. And so all of these others will give zeros. So the table will be the same for each of these expressions. We next turn to logic gates and Boolean algebra. In particular, if we have an inverter, that's represented by x conjugate. What about an OR gate? That's just a Boolean sum. How about an AND gate? That's simply a Boolean product. So we will use these logic gates to construct various circuits. In all of these circuits, the outputs will depend only upon the inputs, which means we're not going to take advantage of any memory storage. Also, for each of our gates, we're going to allow ourselves to have multiple inputs. For instance, we could have x, y, and z going into this AND gate. Okay. Or we could have x, y, and z going into some OR gate. So in this next example, I want to design a circuit that outputs x conjugate plus y times x. So we have an AND gate here, but we have this complement first. So x goes into the complement, and y and the x complement go into this OR gate. Then we need another version of x to come up here to go into an AND gate, and this should output here x conjugate plus y. We have x coming in here. This is an AND gate, so it's x conjugate plus y times x. What if all we know about a circuit are the values and let's suppose the outputs are 1, 1, 1, 0, 1, corresponding here, 0, 0, 0. The only places where we get ones on the output are these here. So this one is, so one way to express this function is as, well, x, y, z, x and y and z are true, will output a 1. But or x, y, but z is not true, note that these two terms together can be combined into xy times z plus z bar. Z plus z bar is always 1, regardless of the value of z. So if this is 1, these two terms reduce to just xy. We'll combine these terms in a minute. The remaining terms are x y bar z here, or x bar yz. So perhaps a simpler representation is xy plus x y bar z plus x bar yz. It follows then that one possible circuit representation will have xy as an AND gate. You'll have xyz, y going into the complement here, and all of these going into an AND gate. And then we need another one of these. I can write it over here. XYZ, X going here. All of these going into an AND gate. And then all of these leading into an OR gate, giving the sum of these three terms. We can use these types of circuits to construct adders, devices that will add binary numbers. Now in binary you only have zeros and ones, and so numbers are expressed like this. 0 is 0, 1 is 1, 1 0 is 2, because when you add 1 to 1 you have to carry this 1 over and then get a 0 here. 1 1 would be 3. If you add 1 to this you'll get 1 0 0, which is 4. And one way to think about these numbers is here you have 2 to the power 0. Here you have 2 to the power 1. This number is 2 to the power 1 plus 2 to the power 0. 2 to the power 1 is 2. 2 to the power 0 is 1. 2 plus 1 is 3. And this one is just 2 to the power 2 plus 0 on the other ones. So this is 4. All right. How do you add numbers in binary? Let's do it by example here. Let's suppose we're adding 1101 together with 111. We'll go in the usual way. We'll add the last two digits, which gives us a 0 carry the 1. Here we get a 0 carry the 1. This is 1 plus 1 would be 1 0, but we have another one here, carry the 1, and this would be 0 1. By reference back to decimal, this number represents 2 cubed plus 2 squared plus 2 to the 0. This is 8 plus 4 is 12 plus 1 is 13. This number is 2 squared plus 2 to the 1 plus 2 to the 0. That's 4 plus 2 is 6 plus 1 is 7. And we add these, we should get something that looks like 20. What does this represent? 0, 1, 2, 3, 4. It's 2 to the 4th plus 2 squared. 2 to the 4th is 16. 2 squared is 4. You add those together, you get 20. In terms of adding, we'll have sums and also the things that we have to carry. So if I have x and y, we'll have these sums and carries. 1 1 gives you a 0 carry a 1 over to the next digit. 1 0 gives you 1 carry 0. 1 carry 0, 0 carry 0. So in binary arithmetic, if you're adding ones, you'll get a 0 for that digit, but you'll have to carry a 1. Note that in this simple analysis, we are not accounting for any carries from previous sums. And hence, this is called a half adder. It's not the full process, but it'll get us started. As you can see, we're going to have two outputs on this adder. We're going to have the sum output and the carry output. We'll have xy bar or x bar y for the sum output. For the carry output, it's xy. One thing I'd like to note is that this sum output can also be represented as x plus y times x times y conjugate. To see this, we can distribute and then work out this conjugate as x conjugate plus y conjugate plus y times x conjugate plus y conjugate, and then distribute again. X and x bar is false, so we can cancel out those terms, plus xy bar plus yx bar plus yy bar, which is always 0, and so we can forget that term. And so this can be represented by this. To turn this half adder now into a circuit, let's have x and y going into an OR gate. We'll also need both x and y going into an AND gate. We're going to tap out of this, and this will be our carry. We'll have to take x and y and get xy complement, and then we'll feed that into an AND gate. And so our final output will be x plus y times xy conjugate. To construct a full adder, we have to have a carry input from the previous sum of bits. We'll have the new bits that we're trying to add. Those will go into a half adder. The half adder has two outputs. It has the sum and the carry. But this sum output has to go along with this carry, and we have to add that carry onto this new sum. So we'll have another half adder, which has its own sum and carry. This will be the actual sum output, but we're going to have to combine these two carries. One thing to note is that down here for this half adder, if you get a carry, then the sum must be 0. So you have 0 going into here. The best you can do is have a 1 coming in here, giving you the sum, but the carry here will be 0. So if the carry here is 1, then the carry here is 0. If the carry here is 0, the sum could be here 0 or 1. That 1 coming into here, you have a carry, which could be a 1, giving you a sum of 0 with a carry of 1. Or if the carry was 0, you have a 1 coming in here. 1 plus 0 gives you 1 with a carry of 0. So either way, it's going to be this or this coming out. What comes out is the new carry. We'll call this initial carry Ci. The new carry is going to be Ci plus 1, the next carry, And these are the bits going into the sum at the ith level when we're adding a whole bunch of bits together. Now suppose we wish to add binary digits like this. We'll add these up. We'll get a Z0, Z1, Z2, and because of the potential carry, we may have a Z3 as well. When we add these first two digits, there's no carry going into this sum. So we can take those and put them into a half adder, which produces a sum and a carry. These next digits take the x1 and y1 along with this carry, and that goes into a full adder. This produces the sum z1 plus another carry. Then we'll take x2 and y2 along with this next carry that goes into a full adder, which outputs the sum z2 along with the carry, which will be the z3. So as you can see, we can use our understanding of Boolean algebra to construct these circuit diagrams that allow us to add numbers in binary arithmetic, and that's the basis for the whole digital age that we live in.